oxygen and nutrients, and it's very important. And so anything that disrupts that coronary blood flow is very serious because we have to keep the heart beating all the time. So that's one of the issues. Well, our coronary blood vessels, our coronary arteries, if you bind norepinephrine to alpha adrenergic receptors, you get vasoconstriction. If you bind norepinephrine or epinephrine as a hormone, for either of these, to the beta receptors, you get vasodilation. So you do get some sympathetic control over this blood flow in the coronary artery. However, most vasodilation is intrinsic, meaning right there in the blood vessel. Metabolites increase is the most potent vasodilator. So as the muscles are using up glucose and other things, breaking it down to carbon dioxide and water, making ATP, these metabolites cause vasodilation. Increases in carbon dioxide, potassium ions, adenosine, and then a decrease in oxygen. All of these act directly on the smooth muscle in the wall of the coronary artery to cause vasodilation. And so that's our main vasodilator. When we look at the coronary artery blood supply, what happens if it gets compromised? Well, what can compromise it? A lot of times it's atherosclerotic plaques in the wall. Or it could be an embolism where a plaque or something has broken off and then lodged in the coronary arteries. This, if it's sudden, can cause a myocardial infarction, a heart attack. If it's slower and it's just sort of occluding, blocking the blood vessel, and that's going to, it could eventually cause a heart attack, but it could cause ischemia. Ischemia, what's that? That is a decreased blood flow. Ischemia is a decreased blood flow. Now here, this shows a coronary artery, and we see it's kind of pinched right there. That is being blocked. It's slowly getting blocked. In this case, they took a stent. You take the little kind of a wire thing, and you feed it down into the coronary artery where the blockage is. You push it through, and then it pops open like a spring, and then that pulls it open, and you can get the blood flow back. Like here it is back, blood flow. These have a lot of advantages, but they can also have some disadvantages. Sometimes they fail after a while. But it certainly has its advantages. Another thing you can do is you can try to bypass the blockage. And we call this a coronary bypass. You usually take a vessel, it's often a vein, from the leg of the patient or the arm of the patient or something. You take part of that and you connect it to this side of the blockage and then to that side, and you bypass the blockage. So it's called a coronary bypass. You could have a single bypass, or you could have a double bypass, or you could have a triple bypass. So if somebody's had a triple bypass operation, that means it's been done 3 times they bypass. Quadruple would be 4 times. So you're bypassing a lot of things there. So these are ways to try to solve the problem. When we look at arteriosclerosis or atherosclerosis, let's take a look at this and then we'll talk about it some more.
Cholesterol is a substance produced by the liver. Animal products are rich sources of dietary cholesterol. Cholesterol is carried in the blood by 2 major lipoproteins, low-density lipoproteins, LDL, and high-density lipoproteins, HDL. Cholesterol is a substance produced by the liver. Animal products are rich sources of dietary cholesterol. Cholesterol is carried in the blood by two major lipoproteins, low-density lipoproteins, LDL, and high-density lipoproteins, HDL. HDL is also called the good cholesterol, and LDL the bad cholesterol. This is due to the fact that HDL helps deliver cholesterol to the liver from the body, including the arterial wall, whereas LDL, on the other hand, delivers cholesterol from the liver to cells in the body, and excess which is deposited in the arterial wall. Once the cholesterol requirement of the cells is met, the extra cholesterol may build up along blood vessel walls as plaque. People with high levels of LDL are at increased risk for atherosclerosis, since they deliver more cholesterol to artery walls. On the other hand, increasing levels of HDL protect against atherosclerosis. Plaques are of two types, hard and soft. Hard or stable plaques have relatively thick fibrous caps. Soft or unstable plaques are vulnerable to rupture without warning. When the soft plaque bursts, it triggers the formation of a thrombosis in the artery at the site of the rupture and restricts the flow of blood, causing a potential larger block in the lumen. Some risk factors cannot be modified, such as advancing age, gender, family history, and menopause. Advancing age is strongly associated with atherosclerosis and heart disease. Atherosclerosis is more common in males till middle age, after which the risk becomes equal between both sexes. Individuals with a family history of cardiovascular disease are at a greater risk when compared to those without. Menopause in women increases the risk, possibly due to decreased levels of estrogen. The major modifiable risk factors are high blood cholesterol level, the optimal level of total cholesterol less than 200.
Okay, let's kind of talk about that a bit before we get to this next one. So just to kind of summarize, cholesterol and some other fats, because they're nonpolar, they need a protein carrier to be carried in the plasma in the blood. And so you have different types of carriers, which are basically classified by their density. So we have low density lipoproteins that are carrying fat, cholesterol, etc. We have high density lipoproteins. We have some others, very high density lipoproteins, etc. But these two are particularly important for what we're discussing right now. Now, LDL, as you heard, we usually call that the bad cholesterol, the carrier, and HDL, the good. And the reason is, essentially, HDL, they both take cholesterol to the liver. But when you have enough cholesterol in the liver, HDL still takes it to the liver where it's metabolized. LDL takes it to the cells and to the lining of our arteries, and it can put it inside the lining. Now, it gets a little more complicated than that. Usually, atherosclerosis is initiated when you have a little damage to the smooth endothelial wall of the artery. You get a little nick in it. And then it makes a place where you can deposit more cholesterol and fats, and it starts making a plaque. And again, you can have a hard plaque, which is stable, but it narrows the artery. Or you can have a soft plaque, which can break off and cause an embolism further down. So those are some of the issues that we would have. So generally we want to keep our LDLs a little lower and our HDLs a little higher and our total cholesterol under 200. So that's kind of the idea of it. Now, when we look at the risk risk factors, a number of them were mentioned there. Age, because our arterial walls get more rigid and less, they stick, stuff sticks to them of the endothelium a little more as we age. They get less elastic. And then genetics can certainly play a factor. That can play a factor in our cholesterol levels, because our livers make cholesterol. It's not just in the food that we eat. And the food that we eat certainly has an impact as well. And then you probably caught the reference that men have a higher risk and than women until women reach menopause. And after menopause, the risk sort of becomes about the same. And estrogen is thought to give a protective cardiovascular role for women. And so if the estrogen levels drop, then your cardiovascular risk goes up. And so that's why we sort of have to keep an eye on postmenopausal women. That's a risk factor that can happen. So that's atherosclerosis. Now, anything that causes the heart to fail can give us a diagram like this, an effect like this. We can call this congestive heart failure, and we'll explain more what we mean, but heart failure can be sudden if you have a myocardial infarction, or it can be gradual. A myocardial infarction, just to define those terms, myocardium means the heart muscle, infarction means tissue death. So myocardial infarction means tissue death. If you get ischemia for any reason, you can get myocardial infarction. If you have too little oxygen coming to the muscle cells, it can cause them to die. Depending on how much of the tissue dies and if it's in a critical position or not in the heart, it could lead to death, or it could lead to diminution in capacity, but not death. So there's a gradation to that. Now, if we look at this is our old relationship. We're looking at end diastolic volume, the preload, if you will, and this is our normal slope along this kind of greenish line. And so if your end diastolic volume goes up, your stroke volume goes up. Remember that since stroke volume and cardiac output are directly proportional, we could also say that our cardiac output goes up. Now, this is needed. Here's our normal resting value, maybe about 70 milliliters for stroke volume. That would transfer into about 5 liters for cardiac output, 5 liters per minute. Okay, stroke volume is 1 beat. Just to convince ourselves of that, if you take 70 milliliters per beat and your heart is beating 70 times per minute, we'd multiply those to get our cardiac output. Well, that would be 4,900 milliliters, about 5 liters, okay? So when we say that we're at about 70 milliliters, let's say, that our normal resting cardiac output would be about 5 liters. Is that all right? Okay, so that's what we're talking about there. Well, if you want to exercise, if you want to increase it, you can increase your end diastolic volume, and you can increase your stroke volume, and you can increase your cardiac output, and along this slope of the line, and that's fine. However, if your heart is failing, congestive heart failure, you go from this slope of the line to the orange slope. So you drop down here. So your normal resting value, your stroke volume, is much diminished at the same end diastolic volume. And if you want to exercise, look at it, you have to go all the way up to 200 milliliters for an end diastolic volume. You'd be way up here for a stroke volume on this slope, but you're barely back to normal for your stroke volume and your cardiac output. In other words, you have much less reserve in a failing heart. And you could, with extra work, get it back to a normal resting cardiac output, stroke volume, cardiac output, but you have very little reserve if you need to exercise or climb the stairs or do anything like that. And so your failing heart is giving you much less ability for the person to put any additional output, cardiac output or stroke volume. So what is the cause of these congestive heart failure? Well, myocardial infarction, congenital defects. We talk about valves, some of the valves. This could be congenital, or it could be acquired later on in life, and we could get valvular insufficiency that we talked about, or valvular stenosis. That can cause hypertension. That means a high blood pressure at rest, so that every time the heart is beating, it has to push against the greater afterload, and over time that can wear your heart down, and you can get congestive heart failure. If you have disturbances in your electrolytes, potassium, calcium, and the like, and so these are problems that can cause congestive heart failure. Why do we call it congestive heart failure? In congestive heart failure, you're not putting out as much blood, so blood is getting backed up. Let's think about the left side. In the left ventricle, you're supposed to put out, let's say, 5 liters of blood, or 70 milliliters a beat per stroke volume, 5 liters per minute of cardiac output. But if your heart is failing, it may not be able to put out that much. And so some of the blood stays in. You have a lower stroke volume, a higher in-systolic volume. Okay? You start with an in-diastolic volume, and then you put out the stroke volume. But if you don't put out as much, you have a higher in-systolic volume. It stays in the heart. So then, as your filling is trying to come in from the lungs through your left atrium, now the filling, you have some back pressure, if you will. It's not coming in. So the blood is back into your lungs, into your pulmonary capillaries. And if you have more blood in the capillaries and the pulmonaries, more pushes out of the capillaries into the interstitial space, the tissue space. And that we call edema. In that case, it would be pulmonary edema. And now, okay, our lungs are getting congested. So we have too much fluid in the heart, and now we have too much fluid in the lungs. So if we're trying to move oxygen from the alveoli into our capillaries, it has a bigger diffusion barrier, because now you have all this fluid in there. It's kind of like getting pneumonia or something. You got too much fluid in there. So you're not getting as much oxygen into your blood, and you're not getting as much cardiac output. You're decreasing the amount of oxygen delivery to your cells, and that's where you're getting into these problems. So we call that congestive heart failure. Over time, the heart can enlarge, hypertrophy. Now, if the heart is enlarging because it's getting stronger and the muscles, cells are getting bigger, that's good. But if it's hypertrophying because it's getting weaker and the fluid in there is expanding and pushing it out, you have more fluid inside the heart and it's making it an enlarged heart. Then on the x-ray or something, you'll say, oh, you've got an enlarged heart, not for a good reason, but a bad reason. It means that the heart is starting to fail because it can't get all that fluid out that it's normally supposed to. So what do? Well, digitalis is going to try to give you a greater contractility of your heart. Vasodilators are going to try to decrease your blood pressure, the afterload that the heart is working against. Diuretics make you pee more, and that decreases your blood volume, so it decreases the load that the heart has to pump against. So these are some of the things that might be used to try to treat congestive heart failure. Now, if there's a blockage, you also have to perhaps do a coronary bypass or something of that nature to try to fix the underlying problem. Do you feel okay about that? Questions or anything you want to chat about?
Did you say digitalis was?
Digitalis is a medication that increases the contractility of the heart muscle. So even if your heart muscle is not working as well, it's giving you a little bit of an extra contraction. Epinephrine can do that as well, but epinephrine is usually only used short term. Digitalis, the patient could take for a longer period. They put it under their tongue usually and dissolves it. So if they're ever getting angina, heart pain, or whatever, then they take some digitalis and it increases the contractility, so the heart is pumping stronger. Yeah, so that's the idea. All right, well, that sort of finishes up the heart. We're moving to our last section, which is the blood vessels. And we'll remind ourselves that we have two circulations. We have the systemic circuit and the pulmonary circuit. For now, we're primarily going to be interested in the systemic circuit. The systemic circuit goes from the heart to throughout the body, and it leaves with oxygenated blood from the left side of the heart, and it comes back to deoxygenated blood into the right atrium. When we do the respiratory system next chapter, we will do a little bit more with the pulmonary circuit, because that's when we're bringing deoxygenated blood from the right side to the lungs and then delivering oxygenated blood back to the heart. But let's focus more on the systemic circuit for now. Systemic circuit, we have these major vessels, the arteries, arterioles, capillaries, venules, and veins. And we'll see that we have some subtypes of the arteries and subtypes of the capillaries and things of that nature. In the systemic circuit, in both circuits, arteries carry blood away from the heart and veins carry blood towards the heart. But in the systemic circuit, arteries carry oxygenated blood and veins carry less oxygenated or deoxygenated blood. The capillaries in the systemic circuit go throughout the cells of our body, and we deliver oxygen to the cells to make energy, and we pick up carbon dioxide, a byproduct of cell respiration, and we return it back to the heart and eventually to the lungs. So this is the role of the systemic circuit. We notice that we have a difference in cross-sectional area and a difference in velocity through these blood vessels. You may be quite surprised to see that the aorta has this relatively low cross-sectional area. Well, what are we talking about? The aorta is the biggest vessel in the body, but there's only one aorta. The capillaries are very small, but we have thousands and thousands of capillaries. So the idea is the total cross-sectional area of our capillaries is much greater than our aorta. So as our cross-sectional area increases because of all this branching, the velocity decreases. So the velocity in the aorta, where blood is being pumped from the heart, from the left ventricle, the velocity is pretty high, but then it decreases as it branches and branches and branches. And so the velocity in the capillaries is quite low. And then it slowly starts to rise as you're taking the blood back to the right side of the heart in the systemic veins. We also have pressure in the artery system and through the rest of the blood vessels. In our systemic, arterial, and our pulmonary circulation, our arteries have a pulsating pressure. And we're quite familiar with this. We know that we have a higher and a lower blood pressure. The higher one we call systolic and the lower one we call diastolic. We get those names simply from the fact that systole is the name we use when the heart muscle is contracting. And most of that time you're pushing blood out into the blood vessels. Diastole is when the heart muscle is relaxing. And so the pressure in the arteries is greater when the heart is pushing blood out into their arteries than it is when it isn't. And so we have systolic over diastolic. A lot of times we say our blood pressure is about 120 over 80. All we're saying is it's 120 systolic over 80 diastolic. What are the units? Millimeters of mercury are the units in that, so that's what we're measuring. We can use a sphygmomanometer and blood pressure cuff, and we can detect. We put it here, we squeeze off the artery, the brachial artery, and then we let it move slowly, and as we hear it coming through, the first sounds we hear are systolic, and then we hear a diminution of sound or a cessation of sound, and that's diastolic, and then we can find that. Now, here is this pulsating blood pressure, and of course it goes way down, and we know in the veins, the blood pressure is much less. When we go in and get some blood drawn from the vein, it's just a little pressure coming in. If you hit an artery, believe me, you'll know. It'll really come. When I was in graduate school, I worked as a venipuncturist part-time to make extra money, and twice during all that time, I hit an artery instead of a vein, and I knew right away because it really comes out. And your arterial blood is much redder, pinker. Your venous blood is purplish kind of color. And that's because venous blood is, the hemoglobin is less oxygenated, less oxygen saturation, and the arterial blood is more oxygen. So anyway, you know right away. You have to really hold it if you hit an artery because it's high pressure, and you have to hold it for 15, 20 minutes with pressure to make sure it's not going to keep bleeding out. Or with the vein, they put a little Band-Aid or a little something around there and wrap it around a little bit, and a few minutes later you can take it off, and it's okay, right? So that's what's happening there. So you have this pulsatile effect. Now you notice that the pressure in the systemic circuit is much higher than the pressure in the pulmonary. That's because the pulmonary circuit is a lower resistance, lower pressure system. And so we'll see that. Now when we look at the arteries in the systemic system, we can subdivide them into two main categories, the elastic and the muscular arteries. The elastic arteries, both of these have some smooth muscle in their wall, but the elastic arteries have quite a bit more elastic tissue. And the advantage of that is when you have this pressure wave coming from the heart, it spreads them out, and then they recoil. And that pushes the blood away from the heart. So our very largest arteries, like the aorta and the carotid arteries and that, those are elastic arteries. So the blood pressure comes in, stretches them, and then they recoil, and that pushes blood away from the heart very quickly. Our muscular arteries, sometimes they're called distributing arteries, because those are our major arteries that carry the blood from the elastic arteries down through the rest of the body. They have smooth muscle in the wall. They have a little bit of elastic, but mostly it's smooth muscle in their walls. These can vasoconstrict or vasodilate, and therefore you can shunt blood to different places, and you can also control your blood pressure to some degree with that. This shows you the elastic arteries where they're being stretched out during systole, and then they recoil during diastole. Now when we look at the pressures, we see here the systolic pressure in this example is about 125 millimeters of mercury, and the diastolic pressure is about 75. Now if you were just looking at that, and you wanted to calculate the mean arterial pressure, what would you, if that's all the information you had, how would you calculate the mean arterial pressure if you knew the systolic was 125 and the diastolic was 75? What's the mean of those two? The average. See, working out in your head. It's 100, right? 125 plus 75 is 200 divided by 2, right? But that's not our mean arterial pressure. Why not? There's a nice little reason. We spend about 2/3 of the heart cardiac cycle in diastole and only 1/3 in systole. So the diastolic value has more of an effect on the mean because we're in diastole for a longer period of time. So we can't just do a simple average like adding the two together and dividing by 2. We have to use a more complicated equation. If you've done any of the case studies yet, you might run into this equation. This is one that you might use. This is mean arterial pressure, and we use diastolic pressure plus 1/3, and this is in parentheses, so we do that first. The systolic pressure minus the diastolic. So we take 125 in this example minus 75 divided by 3 plus 75, and that's approximately 92. Notice that 92 is not 100. It's lower than 100. It's because the diastolic has pulled it down because we're in diastole for a longer period of time. Does that make sense? Why we get and that's why we have to use a more complicated equation rather than just taking the mean. By the way, this aortic valve closure, that's the incisor. When the aortic valve closes, it gives you that little uptick because that closure of the valve causes a little pressure uptick. It can be called the incisura or the diacrotic notch. It has some weird names. Or just the aortic valve closure. But that's that little upswing, very small there between the two. Now, as we age, our mean arterial pressure goes up because our arterial walls get less elastic. They start wearing down a little bit, and so we can get that. And so you can graph the population, and you can find that our mean arterial pressure, systolic, go up as we age. Now, there's other factors that can affect it, impact it, of course, but just age alone will cause your blood pressure to increase. So, but some people, stay healthy and your blood pressure can stay good until pretty late in life. Now, after we go to the arteries, we have the arterioles, which are very much like muscular arteries, except they're smaller in diameter, and they have a higher percentage of smooth muscle in their wall. The arterioles are very good at helping to maintain blood pressure, vasodilation or vasoconstriction, and shunting blood from one place to another. Let me talk to you just a minute about shunting blood. We have a certain cardiac output at rest, let's say it's 5 meters per minute. That cardiac output goes to different parts of the body. 20% usually goes to the kidneys because they're filtering the blood. About 13% to the brain, different parts, okay? We can change that to some degree. After eating, we shunt more to our digestive tract and a little bit less to our skeletal muscles and our skin. If we're exercising, we shunt more to our skeletal muscles and our heart. And so you can shunt it by closing off some of these arterioles and muscular arteries and dilating others. And you can shunt the cardiac output that way. This is why after you've eaten, especially a big meal, you don't want to go jogging right away, right? because you're already shunning blood to your gut to help you die. If you go jogging, now it's saying, oh, now I gotta put it to the muzzle, and like, and you don't feel too good, and then, because you're trying to shun it two places, and so it's not so good. So we usually try to maybe do a little light walk or something after eating, but we don't want to be running or something or playing basketball or something right after. We want to wait a while. What are some of the factors that affect the radius? We have vasoconstrictors and vasodilators. For the nervous system, sympathetic, that's norepinephrine, is going to be a vasoconstrictor. Nitric oxide is a vasodilator. For hormones, we have epinephrine. Now here's the weird effect. Epinephrine binding to alpha adrenergic causes vasoconstriction. Epinephrine binding to beta-2 adrenergic receptors causes vasodilation. So it really depends on how much of these two are expressed at any given time. If you express more alpha, you're going to have more vasoconstriction. If you express more beta-2 in those cells, you're going to have more vasodilation. Other vasoconstrictors, hormones, angiotensin II. Vasopressin, you may remember, is another name for antidiuretic hormone. It has a mild vasoconstriction effect. Atrial natriuretic peptide is released from the heart and is a mild vasodilator. Local controls, you can, with more pressure, you can get muscles contracting. A local tissue area, tissue chemical is endothelium from endothelial cells. And then look at all these vasodilators. These are all important. If you have any of these metabolites or a decrease in oxygen, you can cause vasodilation. This is probably the most important, just like in the heart, these vasodilators. When we get to our capillaries, these are the smallest blood vessels. They're only one endothelial cell thick, and this is where we have the exchange. Oxygen, nutrients with some fluid go out of the capillaries to the cells. Carbon dioxide and metabolic waste, CO2, for instance, and water, a little bit of fluid comes in at the other end of the capillary. So this is a very important area of exchange. Capillaries, only one endothelial cell around them. As you go along, and they have this little lumen. A lot of times, some of the capillaries are so small that the red blood cells have to queue up, line up to get through one at a time. The red blood cells are about 7 microns, and so they have to go single file through the capillaries because they're that small. Sometimes they even have to squeeze their way through. When you look at the hamster cheek pouch, the microcirculation, you'll see some of that circulation, and it's kind of fun seeing that. Three subtypes of capillaries: continuous, fenestrated, and discontinuous. These three, they're all permeable, but these three are on a gradient from the least permeable is continuous, and the most permeable are the discontinuous or sinusoidal. So they're in different places. Again, they're all permeable, but the discontinuous are very permeable. The continuous are in muscle, lungs, adipose tissue. The fenestrated are in the kidneys, endocrine glands, and intestines. And the discontinuous or sinusoidal are in the liver. They're the largest of the capillaries and the leakiest. You come through from an arteriole and you come down through these little vessels, and you can go to metarterioles, and then you can go to capillaries, and then they come from the capillary beds back to venules and then to veins. Venules are just small veins, essentially. So you go through capillary beds. Sometimes you can close off capillary beds to non-critical tissues like the skin or something for a while. But you don't want to close off capillary beds to the heart or to the brain or places like that, or the kidneys. When you're having one vessel going and branching into 6, you will decrease your velocity. As you're branching, so the velocity here is faster, and you decrease it because of this branching pattern. What are the forces to move the fluid and substances in and out of the capillary? Well, first of all, we need to introduce that we have an arterial end of the systemic capillary and a venous end. The arterial end is connected to the arterioles. The venous end is connected to a venule. So blood is coming from the arterial end into the arterial end of the capillary. And here's our forces. We have forces going out of the capillary and into the capillary. Forces going out of the capillary, we have a hydrostatic or blood pressure force, and forces going in are an osmotic or oncotic pressure. This is due to your solutes, like your proteins and other things that are dissolved in the blood. On the arterial end, the hydrostatic or blood pressure is greater than the osmotic pressure. You also have a slight osmotic pressure in your interstitial or your tissue fluid. It's also in the outward direction, pulling it out. So we're going to add these two numbers up, the outward force, and we're going to sum up with the inward force. So we take 35 plus 3 is 38, minus 28, so our factor favoring filtration, moving fluid out on the arterial end, is about 10 milligrams going out. Now on the venous end, all of our forces are the same except for the hydrostatic pressure. Our hydrostatic pressure is lower on the venous end of the capillary than it is on the arterial end. Instead of being about 35, it's maybe about 15. So now when we sum our forces, we go 15 plus 3 going out and 28 going in. So now we have a negative 10 when we sum out. And this is a absorption force or a negative filtration force. We're going back in. What this means is fluid is going out of the arterial end of the capillary and coming back in at the venous end of the capillary. Well, this is important because oxygen and nutrients go out on the arterial end of the capillary, and carbon dioxide and other metabolites come back in on the venous end of the capillary. Now, it's not an exact 100% fidelity. What do I mean by that? Of the fluid that goes out, only 90% approximately comes back in on the venous end. What happens to the other 10%? It comes through our lymphatic vessels and goes through our lymphatic vessels, through our lymphatic nodes and all that, and then eventually dumps back into the general circulation. Okay, so that's why we don't have a complete fidelity there. Now, if we change these values, what if we had somebody with liver failure or liver problems and they weren't able to make enough proteins like albumins, which exert an osmotic force, don't they, that we talked about when we talked about the blood? Well, if we don't have as much proteins, we're going to have a decreased number here on osmotic or an oncotic pressure on both sides. What that means is more fluid will go out and less fluid will come back in, and we'll get excessive fluid in our interstitial or our tissue fluid, and we'll get edema. We're out of homeostasis with our osmotic gradient because we're not making enough proteins that go into the blood, into the plasma. We'll finish up with this little reminder. A lot of times they use slightly different values for the names, so don't worry too much about that. But this gives you the idea of it again.
At the arterial end of the capillary, the net filtration pressure is equal to the net hydrostatic pressure minus the net osmotic pressure. The net filtration pressure is 13 millimeters of mercury. This causes fluid to move from the capillary into the interstitial fluid. At the venous end of the capillary, the net filtration pressure is equal to the net hydrostatic pressure minus the net osmotic pressure. The net filtration pressure is minus 7 millimeters of mercury. This causes fluid to move from the interstitial fluid into the capillary. Approximately 9/10 of the fluid that leaves the capillary at its arterial end re-enters the capillary at the venous end. About 1/10 of the fluid passes into the lymphatic capillaries and returns to the bloodstream via the lymphatic system.
Okay, so it depends which capillary, which numbers you're going to use. Don't worry about memorizing numbers here. If we give you, do this summation, we'll give you numbers and just know how to summate them up. And that'll work, okay? Don't worry about it, because they vary from the different capillaries, so. Okay, so on Monday, we will finish the rest of this chapter, and then we'll go to the respiratory.